are really good.
No. So I'll be watching this. This bar right here is equally black and white. So if white, the challenger, gets an advantage, the computer is going to show this bar go up. If it stays like, even if it goes up to here, like nothing big is happening. But if that thing goes up to like here, then basically he has a winning position on the board. So I just want to be able to see that bar. Okay.
People are all going to start cheering.
So yeah, like in the middle of practice. Go.
Yeah.
Will it actively show
It's like
movement on there?
Yeah, we'll see the. Oh, they've already moved. Okay. So
Let's go.
calm down, everybody. Calm down.
Do anything cool for Thanksgiving?
Yeah, just family stuff.
If the challenger wins, we all get 100 on
Yo, let's go.
If the challenger loses,
All right,
we all have to take the
let's get down to business. I think that's on. Yeah. Okay. All right, we have a lot to do. I apologize for the chessboard, but we're going to keep it here.
Hey, I'm sorry, were we supposed to be done with A4 by today?
No, today, yes. We'll finish 8-4 today.
Okay, cool.
All right, so there was an example I wanted to do. Where is it? I don't believe, just double check your notes. I don't believe I did this example. Oh. Yeah, so the American had the other day, he had a move where it took him 30 minutes to make his next move, the challenger, and yeah, they have it 100 minutes. Yeah. Anyways, he had a move, and the computer was sitting like this pretty much during the first move, or during his move, and then about 15 minutes into his move, the bar went way up, and the computer found that he could win in 37 moves.
The computer?
The supercomputer. And anyway, he didn't find the move, and it was a draw, but afterwards they told him, and both players couldn't believe that there was a checkmate out there in 37 moves. And anyway, so, all right, let's get to this. All right, here we go. What in the world are we doing before Thanksgiving? Alternating series test. Alternating series test. So if you have a series that's alternating, we actually kind of like alternating series a little more than regular series because the test for convergence is easier than the other tests. So do we remember what the test is for this? Alternating series test. There are two things you have to show. What do we have to show for alternating series? That B sub n is greater than or equal to, right? Greater than or equal to, or strictly greater?
No, it's greater than equal.
Yeah, so decreasing, and then we have to show that the limit as n goes to infinity of B sub n is 0. And remember, B sub n is the positive part of the sequence within the series here. So if we rewrite this as -1 to the n times 1 over n factorial, then the B sub n is this part right here. All right? So let's do the first part. Let's show that this is a decreasing sequence, B sub n. So how do we show that? We need to check that that's true. So that means I need to show that 1 over n factorial is bigger than or equal to 1 over what? Yeah, well, we'll say n plus 1 factorial, which is different than n factorial plus 1, right? N factorial plus 1 is not equal to n plus 1 factorial. These are not the same things. Okay, so we're replacing the n here with n plus 1. Is this okay? And now we kind of cross multiply. And then what are we going to do there? Is that true? Remember, we're checking, is this true? It should be, right? I mean, this should be, but I could actually go one step further. I could rewrite n plus 1 factorial as n plus 1 times n factorial. That was one of the properties of the factorials. I think I showed you that property, and I said, don't forget this because we're going to use it. N plus 1 factorial is actually n plus 1 times n factorial. Are y'all okay with that or not? Because we need it quite a bit. Just real quick, show it again. Just think about it this way. If I say 4 factorial, we know that's 4 times 3 times 2 times 1, right? But that's the same as 4 times 3 factorial, because this right here is 3 factorial. But that you could have done that with any number. 7 factorial is 7 times 6 factorial. Make sense? Yeah. So n plus 1 factorial, you're peeling off the n plus 1, and then it's everything down from that. So this is like n plus 1. So there's n plus 1. And then this right here is everything else down. Make sense? Okay, now if I do that, I can divide both sides by n factorial. I get n plus 1 is bigger than or equal to 1. Right? I'm dividing both sides by n factorial. And then that means n is greater than or equal to 0. And that's true. Okay? I know we're jumping right into this, we just got back, but how about this last one right here? The second thing we have to show is the limit as n goes to infinity of 1 over n factorial equal to 0? Should be, right? We have a fixed number on top. The denominator is just going to get huge, and so this will be checked. So this is a convergent alternating series. Yes?
So are we basically looking at like factorial almost like exponential?
We're looking at factorial almost like 1 over n. I mean, because really that's 1 over n times n minus 1 times n minus 2, right, all the way down to 1. So if n gets huge, right, this just becomes a huge number times that huge number plus minus 1 times that huge number minus 2, so it's still going to be big. Does that make sense? Okay. Now we need to establish a couple of definitions. All right. So the first definition here is something called absolute convergence. Given a series, okay? So this is not necessarily an alternating series. This is just a series, all right? Given a series, if the sum of the absolute value of these guys, right? So this is like the sequence. Adding them up is the series, right? If you take the absolute value of those guys, if that converges, then the original series is said to be absolutely convergent. And so the way to think about it is that if you have a series and its absolute value converges, then it is called absolutely convergent. So, next thing. Conditional convergence. If you have a series and it converges, but the absolute value diverges, then the original series is said to be conditionally convergent. I'm going to give you examples of these, all right? And while we have this up here, let's just throw one more thing up here, and that's going to be a theorem. Theorem says if this converges, so does the series itself, like that. Okay. So let's just recap this because these can be confusing first time you see them. Let's say we have a series, we don't know what it does, all right? This could be an alternating series, this could be just a regular old series, whatever. We have some series, we don't know what it does. Well, if the absolute value of this converges, then we will call that absolutely convergent. Now, if we have a series that converges, we know it converges, but when you take the absolute value, it diverges, then this series up here is said to be conditionally convergent. This one is called conditionally convergent. Now, if the absolute value within a series, if that converges, then this original series also has to converge. All right, let's try and do a couple of examples. Let's take a look at the example we just did. And then you can tell me what classification we can give it. So let's take a look at this one right here. All right. So that's the original series. Did that converge? Did this thing converge? Yes, it did, right? It converged. All right. Did the absolute value of it diverge? Well, we never looked at the absolute value of it, did we? Right? Okay. Well, let's take a look at the absolute value of this one. So we all know right now this converges, right? We just did this one. Okay, let's take a look at the absolute value. This would be the same as just 1 over n factorial, right? Why is that just 1 over n factorial?
Absolute value can be
When you take the absolute value of the numerator, right, this numerator is going to be either a 1 or a negative 1, regardless of what n is. So because of that, if I'm going to take the absolute value of it, it's just going to be 1 on top, right? On the bottom, since n factorial is already positive, the absolute value is just n factorial. So does this converge? Well, how would we show it converges? Well, okay, so this is like the new series we're looking at here. If I want to know if that converges, you can do the nth term test first, right? And that goes to 0, doesn't it? This thing goes to 0, which tells you nothing, right? That tells you nothing. So now you have to figure out what test you want to use. Comparison? How about this one? I'll cut down on time for us. How about we do a limit comparison? No? Well, if we do a limit comparison, what are we going to compare it to, though? That's the problem, because we have to know what it does.
Would you integrate a factorial?
Man, I picked the wrong example. The thing is, if we use any comparison test, think about this. If we use any comparison test, we have to compare it to something we know, right? What it does? And if I'm going to compare this to something, the only thing that's going to be similar to this one is another factorial, right? And I don't know whether or not a factorial converges yet, do I? Do you all understand? Like, I'm not quite sure what we would compare this to. I think this is actually a good place to put a question mark and say, hey, we don't know. And this is going to make us appreciate the next test that we're going to do. Okay? We're kind of hung up right here because we don't have anything to compare this to. The only other options are, is it geometric? No. Right? Is it harmonic? No. Is it integral test? Well, you can't integrate a factorial. So we're kind of stuck at this point. Do you see that? Okay, so right now I do not know if it is absolutely convergent. I don't know that. Because what does absolute convergence mean?
That the absolute value.
That the absolute value of that converges, right? The fact that this converges does not mean the absolute value has to. Okay, so right now, I don't know this. Is it absolutely convergent? Is it absolutely convergent? We don't know. We don't know. Is it conditionally convergent? Well, does this happen? Yes. Does the absolute value diverge? I don't know. So, conditionally, don't know. All right, now look at this theorem. The theorem says if the absolute value converges, then the original one has to. Well, I don't know what this one does, right? So I can't use the theorem either.
So it doesn't, like,
Oh yeah, no, it doesn't go the other way around, okay? That's very important in mathematics. You can't change the order of an if-then statement. If this happens, then this is true. But it doesn't, we're not saying that if this is true, then that's true. Okay, so let me do a different example. How about we just change that factorial to just n, 1 over n. Okay? Now, we did that in class last time, didn't we? Look back in your notes. That was the alternating harmonic. That was the first example I think I gave you of the alternating series test. I see you shaking your head. We did do that, yes? Yes? It's in there? So this converged.
Sort of. It was slightly different, but yeah. Pretty much.
It was?
Yeah.
Did I peel the 1 over n off to the side or something? Let me see what you
Yeah, it was just to the n plus 1.
Okay, n plus 1. Okay, so we know that doesn't matter, right? N or n plus 1 really doesn't change anything.
Yeah.
Okay, so that converged, right? Okay, now, let's see if it converges absolutely. So if I take the absolute value of this, what do I get? That just becomes 1 over n, doesn't it? And that's harmonic. And that diverges. So if we were to, let me get this limit comparison out of here in this question mark. On this one right here, are we absolutely convergent? No. Because the absolute value didn't converge, right? Are we conditionally convergent? Yes. Because conditional convergence says that the original series converges, but the absolute value diverges. Make sense? Okay, let's look at another one. This one's going to be a little bit tricky. Sine of n over n cubed. Okay, this one is interesting. P series what?
It has to be over a constant.
Has to be a constant over n to a power. Okay, let's first establish a couple of things. You cannot use a comparison test here. Why?
Can't do like a squeeze, like -1.
Yeah. That would be more like a comparison.
Yeah.
Yeah.
Is it because n is inside of sine?
Remember on our formula sheet, Yeah, the n is in sign, but look at our formula sheet. Wrong one. Those aren't formula sheets at all. What did we say about the comparison tests? That when we were doing them, I kind of hid this from you. Remember, it said that these always had to be positive, right? You cannot have negatives in there ever. Ever, right? So comparison test does not work for alternating series, but it's also not going to work for this one because sine of n is sometimes negative, isn't it? Now, this is not an alternating series, though. Why is this not an alternating series? Is it going negative, positive, negative, positive? Not necessarily, because think about sine of n. If you were to graph sine, it would look like this, right? Now, if you plug in 1, you're going to be here, right? If you plug in 2, you're probably going to still be positive, and then eventually, you become negative and then positive. But it's not switching positive, negative, positive, negative, positive, negative. That's alternating series. This one, it does change signs, but it doesn't actually follow the pattern. And not only that, this does not have to be 1 or negative 1, right? It could be any number between negative 1 and 1. So do you all see this is not alternating series either? So we cannot use the alternating series test. I guess what I'm telling you is nothing's on the table here, okay? Nothing is on the table in terms of our tests. Y'all with me? Okay. Yes?
Is it because it could be any value? You said because it could be any value between.
That's right. That's right.
Yeah, alternating would just be like 1 negative
Yeah.
1.
Let's actually, just so we see it, let me see if I have. Let's just type in sine n here. There we go. So take a look at this. Can y'all see this? So like at 1, you're up here. 2, I don't know where you are. Where the hell is 2? Oh, you know what? I'm zoom out a little bit. I need to zoom out. There we go. Okay. Now you can see it. So look where I am. At 1, I'm here, right? That's 1 is up here. So when I plug in 1, I'm here. I'm positive, right? Positive, positive, negative, 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 positive, 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 negative, negative, negative. So do you see that? And then it's also not negative 1, 1, negative 1, 1. So it's not alternating, not an alternating series. Y'all with me? Okay, so watch what I'm going to do. First of all, I'm going to take a look at the absolute value of this, right? Okay, so now I've made that positive, haven't I? Yes? Now I can use comparison test, okay? And I'm going to compare this. I'm going to compare it to 1 over n cubed, which is what type of series? P series. And this P series converges because P is greater than 1, right? All right, so now what do I need to show? I want to show what? What do I want to show in order to use this test? If this one converges, I need to show that the other one is always smaller than this, right? Okay, so I want to show that the absolute value of sine of n over n cubed is less than or equal to 1 over n cubed. Now, do I really need the absolute value on the denominator on the left side? Is n cubed always positive? Yes? Okay, sine of n is not, so I still need the absolute value on that. But I can say over n cubed less than or equal to 1 over n cubed. I want to show that that's true. Is it? Cancel out the n cubes. And what do you get if you cancel out the n cubes? Yeah, I'm trying to squeeze it right in here. So this means that the absolute value of sine of n is less than or equal to 1. Is that true? The sine function is bounded, right, between -1 and 1? But if you take the absolute value of it, it's definitely going to be positive, right? But the biggest it could be would be 1. So this is true. So this is a true statement. And therefore, I've shown that it does what? What does this series do? It converges because we compared it to a convergent p-series. So check this out. We had a series, we didn't know what it was, right? We looked at its absolute value and figured and determined that it converged, right? So this thing converges. Now what can I say about that one? Why? The theorem tells us that if the absolute value of a series converges, then the original series converges. Think about it this way. If I'm saying that I'm trying to add up all these pieces, right? That's when we do a series, we're saying take those and start adding them all up, right? Add them all up. Well, some of them could be negative, right? And some of them could be positive. Well, if we take the absolute value of this, then they're all positive, aren't they? We've made them all positive. And if we're adding all those up and it's converging, then this has got to be less than that, right? Because it's got negative stuff in there also. Does that make sense? So it's like taking away from something that already adds up to be a finite number. I hope that makes sense. But the theorem tells us that that converges. So this converges by the theorem. And that theorem is on your formula sheet. It's the last thing on the bottom of the page, I believe. See that at the bottom? If you take a series, you take its absolute value, right? If the absolute value converges, then the original series converges. Got it? All right.
Oh,
Yes.
so like on it, you'd say it would be okay to just say converges by theorem
Sure.
at the end.
Uh-huh.
Okay.
Yep. Just, make sure you somehow state it so that I know you're using the theorem.
Oh, just kind of put off the side, hey, this one.
Yeah, like once I just, again, need to see that train of thought. All right, y'all ready to continue? We have another test. And this is the big daddy right here. This is the big daddy right here, the ratio test. And this is on your sheet. Couple of great things about the ratio test. Look at what this is saying. If you have a series, right? That doesn't say alternating. It doesn't say anything other than it's a series. It doesn't say that those have to be positive. So in other words, this could have worked for the series we just looked at, right? It's any series. If we have a series, then what we can do is we can take the limit as n goes to infinity of this ratio. So what it is, you know how we were checking before to see decreasing and increasing? This is kind of like the same idea, but instead of doing an inequality like we've done like this, we tried to show that before. But instead of doing this, all we're doing is we're taking these two pieces and we're making a ratio out of them. Okay, a fraction, and we're taking the absolute value of it. It gets its name ratio test from the fact that we're going to set up a ratio. If this limit, okay, this limit, and then you take the absolute value, if that limit equals a number L, then we have basically there's three actual results. Let's see if it says it over here. Yeah, it says it over here. So it says if we take this ratio and get a limit, it will converge if that limit is less than 1. If that ratio is less than 1, then it will converge absolutely. What does that mean? That means that the absolute value of that sequence converges and the sequence itself converges. Both of them. And then if that ratio right here, if the limit of that ratio is bigger than 1 or infinite, it diverges, right? And if it is 1, right, because this is less than 1, this is greater than 1, if it is 1, the test fails. This is the only time the ratio test sucks, is when you get a limit of 1. Then you have to try something else, all right? But let's just see how this test works, and let's do it for that absolute value one, okay? So let's take that one we were stuck on. We had sum n equals 1 to infinity. We had negative 1 to the n over n factorial. Now we know already that that converges, don't we? How do we know that converges? What did we use? Now when we did the absolute value, we couldn't tell what it did, right? But if right now I said, hey, tell me if this converges or diverges, what test could you use? You started class with it. Alternating series test, right? Okay, but I'm going to use the ratio test instead. So this thing in here, that's my a sub n. See, I don't peel off the positive part. For the ratio test, I use the whole damn thing, all right? So what I'm going to do here is I'm going to take the limit as n goes to infinity. I need the absolute value of a sub n plus 1 over a sub n, right? Now please pay careful attention to this because we are going to use this a lot, the ratio test. So let's set this up. The queens are still on the board. It's a good sign that something, once the queens come off, then it starts to simplify, and then it's probably a draw. All right, so here we go. What's the numerator? Because this is my ratio, something over something. So what's my numerator?
Negative 1
-1 to the n plus 1 over n plus 1 factorial. That's this sequence with my n's replaced with n plus 1's, right? What's the denominator? Negative 1 to the n over n factorial. Any questions where that came from? Okay, this is the same as 1 over n plus 1 factorial over 1 over n factorial. Why? Yeah, the negative 1's to the n aren't going to ever matter, are they? Like this is going to be, I'm going to take the absolute value of it, so it's going to be a 1. I'm going to take the absolute value of that, so that's going to be a 1, right? So those don't matter anymore. Okay, and then that's a fraction over a fraction. I can just flip it. This is limit as n goes to infinity of what? Absolute value? N factorial over n plus 1 factorial. Now we're going to use that property of n plus 1 factorial, peel off one piece. And this is going to be n factorial over n plus 1 in parentheses times n factorial. The n factorials cancel. And you finally are left with the limit as n goes to infinity of the absolute value of 1 over n plus 1. And now let n go to infinity, and you get 0. And is 0 less than 1? Yes, so what happens? We have absolute convergence, which means that not only does this converge, right, but its absolute value converges. This test is super powerful. Super, super powerful. Let's do another one. Negative 1 to the n, let's go n plus 1 there, just for fun. Let's go n squared over 4 to the n. Okay, so if we were going to do this, we would have to use the alternating series test before today, right? Alternating series test, because it's an alternating series. We can't, our only other hope is that this is geometric or harmonic or telescopic or something like that, right? It's not? That's not geometric? Oh, we had an n up here. Geometric? No, because of the n squared. The n squared throws everything off, all right? Yeah, if this was not here, if that was a 1 or any other number, then that would be geometric. And I wouldn't even, I would just need to make sure I knew what R was, and then I'd be done. I can move on. But we have the almighty ratio test now. So I'm going to set this limit up. I'm doing ratio. So limit n goes to infinity. Okay. It's going to be -1 to the n plus 2 times n plus 1 squared over 4 to the n plus 1, all over -1 to the n plus 1 times n squared over 4 to the n. I'll give you a second to soak that in.
We can't see, so we have to.
Yeah, I know. You're on the wrong side of the room.
Can you just ignore the -1 when you're doing this?
Could you what?
Can you ignore the alternate?
You could, but I mean, for that first step, maybe just write it and simplify on the next step.
Okay.
I mean, it's not wrong because you understand what's going to happen, but that is technically a sub n plus 1 over a sub n, right? Without any simplification. We're all comfortable with where everything came from? I mean, things that I see that are wrong, n squared plus 1, that's incorrect, right? It's n plus 1 squared. Okay, so now a lot of things simplify, don't they? So let's do this. Limit n goes to infinity. See if you can follow this. This is going to go away and become a 1. That's going to, ooh, this is a big red marker. Look at that. It's probably not going to erase very easy. That's going to go away. So I'm going to have this fraction, right, over this fraction. So what I'm going to do is I'm going to go ahead and write that fraction down, n plus 1 squared over 4 to the n plus 1. I need my absolute value here. And then times, this fraction is supposed to be below it, right? Yeah. So I'm going to flip it now. So I have 4 to the n up here, and on the bottom, n squared. Is that too much, or are you okay with that? You all right? A little bit more. Limit. N goes to infinity. Absolute value. N plus 1 squared over 4 to the n times 4 times 4 to the n over n squared. So what did I do there? Yep, I did this piece right here. I used properties of exponents to split it up into this. That's the same thing, right? We've done that already with geometric series. We've tried to mess around with the exponents. But I did that just so I could get these 4 to the n's to cancel, right? Lots of things went away there. Well, not lots of things. Only that went away. That's not a lot of things, I guess. And then I just expanded that, and I put 4n squared on the bottom. And can you see what I'm going to do next? L'Hopital a few times, right? If you do L'Hopital on this a few times, you should get 1/4, which is less than 1, which means we have absolute convergence, right? So this will converge. What do y'all think about this? I'm only showing you 2 examples, but look okay? Yeah? Yeah? Let's do one more. Let's do one more. What the heck is that? Oh, I didn't see that one. Okay. We're going to do 2 more. Let's do this one. See what happens if we do -1 to the n over n. Yeah, let's do that one. Yeah, just like I said, this thing is not going to want to erase. Look at that. It's left a blood trail on the board here. It's like a permanent marker almost. Now, the problem I just put on the board, didn't we already do that problem? That's that alternating harmonic, isn't it? Didn't we say that that was conditionally convergent? We did, right? So the ratio test, should it work or not? What does the ratio test tell you at the end? That you have what? It'll give you absolute convergence, won't it? It'll give you absolute convergence. Now, that should converge, right? But the absolute value diverges. So does anyone have a guess as to what the ratio test is going to give us? 1. It should. Because it shouldn't show us that we have absolute convergence, and it shouldn't show us that we have divergence. The test should fail. So let's see it fail. See if you can follow me on this. Okay, what have I done?
Oh, you did the ratio, then you multiply by their surface.
Okay, so a lot of times, I would almost say from here on out, I'm going to stop writing a sub n plus 1 over a sub n. What I'm going to do is I'm going to write a sub n plus 1, and then I'm going to imagine a sub n down here, but I'm going to flip it and put it here. Okay, so I've done that flipping step already just to start. Everyone see it? Okay, now a lot of things clean up. Limit n goes to infinity. All you're left with is n over n plus 1, right? Because you don't have to take into consideration, this was negative 1, sorry. You see that here, this right here? Negative 1 to the n. And do you see the problem now? It goes to 1, right? This goes to 1, test fails. So that is a good example of how you have we have a failure of the test, right? This is not telling us convergence or divergence. This is telling us the test didn't work. We already know that this is a conditionally convergent series. This converges, but the absolute value diverges. All right, now let's do another one. This one's a good one. N to the n over n factorial. Let's just go straight to ratio. Limit n goes to infinity. All right, help me out. Who wants to give me the first fraction?
N plus 1 to the n plus 1.
N plus 1 to the n plus 1. Okay, you're off the table now. Who wants the next part under here?
Should be n plus 1 factorial.
N plus 1 factorial. Okay, you're off the table now. Who's giving me the next part right here?
Would it be n factorial over
N factorial over what?
n to the n?
N to the n. Do y'all agree with that? Okay, that is correct. That is setting up the ratio test on that. Notice, you know, the n plus 1 to the n plus 1, kind of weird, but that's what it is. All right. What now? Yeah, this right here can become n plus 1 times n factorial, right? That's this. And the n factorials will cancel. Anything else we can do? How? How?
N plus 1 to the n and then n plus 1.
Good. N plus 1 to the n times n plus 1 to the 1. That's this. That's that split into two pieces. Y'all see that? It's kind of weird, but that's what it is. Like, I don't need to put the 1, but I will. That's a 1 there. Isn't that's the same as n plus 1 to the n plus 1. And then over n plus 1 times n to the n, like that. Because we didn't lose this guy. This guy's still here, right? Okay, we get cancellation of the n plus 1s. And we get limit as n goes to infinity.
Would you then
Pardon?
to n into, would you then put like n into each?
N into each. Oh, yeah, no, you mean like that?
Yeah.
Can't, because it's addition, right? Because like if this was squared, you'd have to, yeah. So unfortunately, that's where we're stuck. We are stuck at n plus 1 to the n over n to the n. Y'all agree? And that's kind of a crappy place to be stuck, but we'll continue. This is the same as limit. N goes to infinity, absolute value. Can I write it this way? N plus 1 over n, all to the n. Since the numerator is raised to the n, denominator is raised to the n, they're both raised to the n, I can just do a fraction to the n. And since the fraction happens to be two terms over one term, can I rewrite that as 1 plus 1 over n to the n? Right, I can do like n over n and then plus 1 over n. Do you all agree? Now I'm only doing that because I'm about to take the limit of that as n goes to infinity, right? Right? Does anybody recognize this? I know in my Cal 1 class we did this, but does anyone recognize what this limit goes to? It's a very special thing. Not quite 1. This goes, look, this is approaching 0, isn't it? But it's 1 plus a number that's bigger than 0. So this number in here is approaching 1, right? It's not 1, it's approaching 1, but the exponent is approaching infinity. So this is what in Cal 1 we would call this an indeterminate form. You have something approaching 1 raised to something that's approaching infinity. We don't know how to do it. Well, in Cal 1 we'd be like, what do we do? So we bring in L'Hopital, we have to do natural log on both sides.
Oh, I hated that.
Yeah, okay. But I want everyone, you're all potentially going to be Cal 2, like have finished Cal 2, right? Everyone here? Everyone here should recognize that limit from here on out and be able to, like, when you see it, know what it is. It's a very special one. This limit goes to E. I'm not going to go through the work for this, okay? I could, but it would take us too much time. All right? That goes to E. So actually, if you wanted to, if someone was asking, you know, like, what's E, you could define E to be that limit. You could say this is a definition for E, if you wanted. It's the limit of that. Absolute value doesn't matter because this is a positive number, and raised to a positive number is all positive numbers, so the absolute value could just go away. Okay? I regret that I don't have the time to show you that limit, but if you want to see it, if you've never seen it, then you can come by my office and I'll show it to you. It's not that big of a deal. Okay, but what's the end result of this then? E is bigger than 1. So this thing diverges. By the ratio test. You could kind of could have seen this in the very beginning if you just would have taken some time to take a look at what this actual series looks like. Like this series looks like this. It's n to the n, right? So it's n times n times n times n times n times n, right? Dot, dot, dot. N of those, there's n n's multiplied over n factorial, which is n times n minus 1 times n minus 2 times n minus 3, all the way down to 1, right? Can you see that other than this one, that one's 1, right? But this number is bigger than 1. Do you agree? Like if that's 10, that's 9. That number is bigger than 1. If that's 10, that's 8, that's bigger than 1. So this is a number bigger than 1 times bigger than 1 times bigger than 1 times bigger than 1, right? That in itself would have failed the nth term test, which we didn't do in the beginning, did we? But it would have failed it. But it would have been hard to show it. So would have had to do some sort of like comparison. But the ratio test worked. We got E. We're happy. We're moving on. Okay? We are going to use a lot more ratio tests, I promise, but there's 2 more tests that we need to at least get down on paper here that we've talked about. So the next one is the root test. This one doesn't come up a whole lot, but we want to know it's there in case we need it. You know what? No, this is the last test. Oh, that was you. I was like, where the hell is that coming from? I thought there was like someone had a flat tire or something in here. Root test. All right, the root test. Let me bring it up on our formula sheet. All right, so the root test, another very powerful test because we can use it on any series. Doesn't have to be alternating, doesn't have to be positive terms. It says that it's almost like the ratio test. It says that we're going to take the limit of something and get L. And if L is less than 1, it converges absolutely. If L is greater than 1 or infinite, it's divergent. And if it's 1, it's inconclusive. So very much the same as the ratio test, right? But the limit is different. What we're going to do is we're going to take what's in here, take its absolute value, and then take the nth root of it. The nth root is the part that's new. That's why they call it the root test. All right, so let me show you how this would work in an example. Yeah. So sum n equals 1 to infinity. What if we had 5n minus 11 over 2n plus 1 to the nth power? Let's see, is that what I want? Yeah. So real quick, if we did, no. Let's just do the root. Let's just do the root test. So I'm running the root test here. What I'm going to do is I'm going to take the limit, Robert, the limit, this n goes to infinity, of the nth root, right? The nth root. The nth term test, we would be done. That's why I said let's just go straight to the root. Yeah, let's just go straight to the root. So if I do the nth root of this, do you see why the nth root is going to be very nice here? Because it's being raised to the nth, right? So when I take all of this to the nth power, right? And I'm supposed to put that in absolute value. Forgot that part. And the absolute value part doesn't matter because everything in there is positive anyway. Well, actually, in the beginning it's not because that's negative, but the roots will cancel. With the root will cancel out the power, and all we have left is the 5n minus 11 over 2n plus 1. And now take that limit, and what do you get? L'Hopital, right? 5 over 2, which is bigger than 1, so this diverges.
So then what if it was like to the nth power plus 1?
If that was to the n plus 1, then you could peel the other part off.
Just make it into like 2.
yeah, so you'd have this to the end, then the same thing repeated over here. And so the root would kill off one, right? And then the other one would still be under a root, but you could take the limit. You'd still be able to get the limit inside to be numbers, so it would still work out. Now, just out of curiosity, this one would have failed with the nth term test in the beginning. But what if I made this 20 instead? 20 right there. Then we'd still have what? We'd have like 1/4 in there to the n. Yeah, that'd still fail. We have to do n squared. I'm trying to think of how the nth term test wouldn't work. So what if I made that n squared? And what happens if you just let n go to infinity here? The inside's going to go to 0, and 0 to the infinity is indeterminate. Oh, no, that goes to 0. Okay, that goes to 0, so we're good. If it goes to 0, that tells us nothing. Is that okay? And then if you ran through this, this would be n squared. Then when you come over here, this would be n squared, and then this would go to 0, wouldn't it? And that would be less than 1, that would converge. That okay? All right. I could tell that was kind of bothering that you could have done the nth term in the beginning. All right. All right, that is it for this section. 8-4, we are done. Now you just get to go and do your homework for this. All right, so what we have now is we have completed this entire sheet. Believe it or not. We have the nth term test that we always want to run. Geometric series only if it looks a certain way, right? P series only if it looks a certain way. Integral test, only if we have to. Only if we have to, right? I mean, that's a pretty long, drawn-out process. Comparison test, that's good. We had the comparison, and then we had the limit comparison, which was really nice. But this only worked with positive series. Then we have the ratio test, which is, like I said, the big daddy. Okay, I like this one a lot. It gives us absolute convergence. The root test is there, okay, if we need it. That one, it starts to give you hints, like on the side. Useful if a sub n involves an nth power, right? Alternating series test, that's really, it's kind of fast to do that one if you have an alternating series. If you can almost see automatically that it's decreasing, like if you can just look at it and see, oh yeah, it's decreasing, then the limit's going to go to 0, you can do that real quick. And then that last one is the absolute value. Absolute convergence implies convergence. All right, that's it. We get to proceed now. Yeah, what's going on over here? Not a lot's changed here. Let's see. Let's take a look here. Whoa. So let's see. So he's on 18 minutes on this move right now. He's trying to figure out what to do next. He's got 1 hour 22 minutes left. The other guy's got 1 hour 35 minutes. There are, oh wait, no. They're not playing online, no. They're sitting in London right now.
They're playing online.
Yeah.
Coolmathgames.com.
All right. No! Where'd it go? There we go.
I haven't seen that.
Download Flash.
8.5. Power series. All right, we finally have made it to power series. So here's a definition. A power series is a series of the form sum n equals 0. So this, for the first time, we're going to start at 0. Now I know that throws a lot of things, a lot of problems into the way I first introduced the idea of a sequence. I said it goes from the natural numbers into the real numbers. I said we start at 1 always.